share my screen. Can you guys hear me, by the way? Hopefully you can. Everybody good? Hang on. I'm going to make sure you can hear me before I start talking to myself. So can you hear me okay?
Yes, ma'am.
Okay, thank you. Okay, so I just want to verify that in every class because sometimes you can't, and I'm sitting here talking to myself for 10 minutes before anybody says anything. Okay, so if you can see my screen here, I had a lot of trouble getting the quizzes integrated into Canvas, and I was just really at my wit's end. I worked on this Monday and Tuesday, I think. Anyway, I finally got it figured out. So I was able to add your Chapter 12 quiz. I haven't added the Chapter 13 quiz yet. I'll hopefully do that today. Or maybe tomorrow. So I'll hopefully have that up soon, okay? And then I need to add your exam 1. Okay, so your Chapter 13 quiz would be due at the end of next week, and then hopefully have an exam from 6, 12, and 13 similar to that. Now, I had sent you an email, but I kind of changed my mind since then. So I had said that I was just going to use the quizzes that Dr. Lang had made, but I think it's better to go ahead and use quizzes from Pearson because they will be more integrated and they will be what you paid for. So I went ahead and added a quiz there. I don't believe that I can give you more than 2 chances per problem, but I think I gave you a couple of chances to take the quiz. So I did finally figure that out. I finally figured out how to get your grades to post on the quiz. So hopefully everything will be working properly now. Okay, so I also had to, where is that? That introduction, that chemistry primer, no, the introduction to mastering. I wanted that to be extra credit, and I kept setting it to 0, and it kept resetting itself to 12 points because it's integrated from Pearson. So I had to move it to a module that doesn't count towards your final grade. So if you go over here and look at, you can't see this, I don't think, but if I go to the assignments, then but you have the group weights somewhere. I think it's under the syllabus. But anyway, you can see that, let's see, that's 0. I think I put your introduction to mastering right there in your dynamic study modules. So all of these are going to be extra credit, but I have to add that at the end of the class. So I'm just going to give everybody a couple of points total if you do these. If you don't do these, then, and that'll be on your final grade, then it won't count against you. It just might help push you over the edge. And it should help if you do a little bit of them to kind of help you understand the problems a little bit. So I do recommend the dynamic study modules, but what I don't want to do is frustrate you to just giving up. Okay, I want you to do the material, understand the material, but not be so frustrated that you just give up. Okay, so I've assigned just quizzes from Pearson. I didn't assign the ones from Canvas, and hopefully I got that worked out now. Okay, so so that's, I just wanted to mention that I have been struggling with the integration. I didn't build the original course, and I'm just really struggling with that integration. So hopefully I've gotten that worked out, and we will just go ahead and move on. So what I want to cover today is just I want to cover unit cells because that all of the problems in this chapter either deal with the Bragg's law formula that we covered last time, or the cubic unit cell. Okay, so only 2 types of problems in this chapter: Bragg's law and cubic unit cell. Okay, so I want to cover unit cells. Then I'm going to cover the problems dealing with unit cells, and they're really not that difficult if you understand the concepts, okay? And then I want to cover as much of the rest of the chapter, if I have time, as I can. So the rest of the chapter is just concepts, but I do want to run through it real quick, as briefly as possible. You may have some random questions that you could probably Google from the rest of the chapter. Okay, so, but I do want to show you how to work all of the problems. All right, so I'm going to begin by using your textbook as a reference because I don't feel that the PowerPoints are sufficient to explain this information. These concepts are a little bit more detailed, so I didn't have time to edit the PowerPoint, so I want to use the book, okay? All right. So there are 7 different types, fundamental types of unit cells. So what is a unit cell? A unit cell is talking about the minimum set of atoms that make up a unit of a crystalline structure. Okay, let's see if they give a definition. I can probably get a better definition here. It's a smallest collection of atoms, ion, or molecules that represent a crystalline lattice. Okay, and then that unit cell is repeated over and over like the tiles on a floor, but in 3 dimensions. So here we have a 2-dimensional representation of a unit cell. So you have this minimum arrangement. Here in this case, we have 4 atoms with another atom in the middle. Okay, and that's repeated. That pattern is repeated over and over, expanding outward in a 2D arrangement. Now, that'll be a 3D arrangement for a crystalline lattice. Okay, so you can see here that the diameter of the unit cell, or the edge length of a unit cell, goes from the center of one atom to the center of the next atom. Okay, so it doesn't go from the edge of the atom to the edge of the atom, and that's key. It's center. It's the center of the atom to the center of the atom. Okay, so we're going to have to calculate that edge length in order to be able to get the volume of a unit cell and that sort of thing. So keep that in mind, okay? So we have 7 fundamental types of unit cells. We have the cubic, tetragonal, orthorhombic, rhombohedral. This is not my field, so I don't even have all of these guys memorized and all their properties. We're going to focus just on the cubic unit cell for this class, okay? We've got hexagonal, monoclinic, and triclinic, okay? So each of these is different. So for the cubic unit cell, which we're going to focus on, the edge lengths, okay, the length of A versus B versus C is all equal. So for a cube, you know, all of the edge lengths are equal, okay? And also all of the angles are 90 degrees. So you're familiar with a cube. So tetragonal is more like it's an oblong, okay? It's not a cube anymore, it's a rectangle, okay? It's a rectangular box. So we've got A is equal to B on one end. Okay, so it's like a square on one end, and then we've got a rectangle on the other side. So B is not equal to C. Okay, but all the angles are 90. It's still square. All right, then next we've got the orthorhombic. A is not equal to B is not equal to C. So all the edge lengths are different, but all the angles are 90. But you don't have to memorize these things. I don't know. I didn't really look at the Pearson quiz yet. I don't know how much they're going to ask you. You might want to just have this as a handy reference when you're taking the quiz, okay? So rhombohedral is A is equal to B is equal to C. So it's like a cube, except the angles are not 90 degrees. Hexagonal, we've got A is equal to B is not equal to C. So again, we've got the rectangular thing, but we have some different angles. So it's kind of like a squished tetragonal structure, okay? So it's rectangular on one side, but it's kind of squished. And then we have monoclinic. A is not equal to B is not equal to C, but the angles are 90. Okay, this is different. And then we've got this other one. So, you know, these are all just different types of crystal structures that you could have that different atoms are going to form. So different atoms, according to their properties, or different molecules, are going to arranged in these structures according to the atoms that make them up, okay? So we had different unit cells. The only one we're going to focus on is going to be the cube because it's pretty simple. All the sides are the same length. All the angles are 90 degrees. But we have 3 different types of cubic unit cells that we're going to focus on, okay? All right, so we have these 3 different types of cubic crystalline lattices. Okay, we're going to look at each one of these. So we've got the simple cubic structure. This is a simple cubic. We have 1 atom per unit cell. I know this looks like 8, but we're going to see why it's 1 in just a minute. Okay, coordination number of 6. That means each atom has 6 other atoms around it. We're going to see a picture of that. Okay, and the edge length in terms of radius is 2r. Okay, the edge length is 2r. So if we know the radius of an atom here, then you can calculate the edge length. The packing efficiency, that means the fraction of volume occupied by atoms is 52%. So we're going to look at that. Then we've got body-centered cubic, okay? It's 2 atoms per unit cell, coordination number of 8 other atoms around each atom, and its edge length is 4r over the square root of 3. We're going to see where this number comes from in just a minute. Packing efficiency, 68%. Face-centered cubic, 4 atoms per cell. Okay. Oh, well, let's back up to the body-centered cubic. We've got 1 atom in the middle of these 8 other atoms, right in the center. That's why it's called body-centered. It's going to say something else about that. All right, we'll come back to that in a minute. Then we've got face-centered cubic down here. We've got an atom on each face. We've got an atom on each face in the center of the other atoms, okay? Its coordination number is 12. There's 4 atoms per cell, and edge length in terms of r is 2 on the square root of 2r. And now, you might want to print this chart or have it handy when you're working your problems, okay? Packing efficiency, 74%, okay? Oh, this is what I was going to say. The different colored atoms do not represent different types of atoms. In this case, they're all the same atom. That's to keep everything simple. All the atoms are identical in these structures, okay? They're different colors just to show just the different arrangement of them, that like the ones in the center, ones on the face, or whatever. So, all right, simple cubic. This is why we only have 1 atom per cubic cell, for unit cell, I'm sorry. It's because each of the edges of this simple cube only make up an eighth of an atom, and there are 8 atoms in the cube. So that means that we have 1 atom per unit cell. So hopefully everybody can understand what I'm saying here. Each of the edges, each of the corners makes up an eighth of an atom. Okay, just an eighth, because the unit cell only goes to the center of each one of those atoms. Okay, each of the corners is an eighth of an atom, and there are 8 of them, so there's 1 atom in the unit cell. Okay, and the edge length can be calculated by 2 times the radius of an atom, because see, they're touching here, so it's 2. I don't know if you can see my cursor. Well, I can't write on this, but anyway, it's 2 times the radius, okay? All right, so that's the simple cubic unit cell. All right, and so we're going to have these numbers. I mean, if you've got your formulas up here, that little chart, so this is not really that difficult to work these problems, okay? The coordination number is 8, meaning each atom has 8 other atoms around it. You can see here this purple one has 8 other atoms around it, okay, that it's in close contact with. All right, and so 1 atom is in the center of this unit cell, and then the other 8 atoms are around it. Sorry, this is the body-centered cubic. This is body-centered cubic. I'm sorry. I got to back up. I lost track of what I was doing. This coordination number is 6. Okay, simple cubic. Sorry about that. Coordination number is 6. It means 1 atom has 6 others around it, and we don't have a picture of that here. It wasn't given. Okay. 1 atom has 6 others around it. Just like this body-centered cubic, the center atom has 8 others around it, and each atom, in fact, has 8 others around it, because each atom at one point forms a center one. each one of these simple cubics has 6 other atoms around it. So that wasn't demonstrated here, okay? Now, the edge length is 2R, okay? And the packing efficiency, that means the percent that is atoms divided by the percent that of the volume of the whole thing. So we're going to come back to that, but the volume of the atom divided by the volume of the unit cell is 52%, okay? Now we're going to the body-centered cubic, okay? Body-centered cubic. This one has an atom at the center and 8 atoms around it, and the coordination number for each of those atoms is 8, okay? Also, it has an eighth of an atom at the corners, just like the previous example, but since it has a whole atom in the center, okay, then there are 2 atoms per unit cell. So an eighth of an atom at the corners and a whole atom in the center means there's 2 atoms in the unit cell. So that's also in that chart. You may need to refer to this chart, okay, to do these problems. This is an important chart to do these problems, okay? And then next we've got, wanted to show you the face-centered cubic real quick. Okay, so that is called the packing efficiency. The packing efficiency is the percentage of volume of the unit cell occupied by the spheres. In other words, it's the volume occupied by the spheres divided by the total volume times 100. Okay, so you can see here that the simple cubic unit cell has a packing efficiency of only 52%. In other words, it contains a lot of empty space. So we're going to come back to this problem in just a minute. I want to look at the some other properties, okay? So here we did body-centered cubic. All right, so let's look at how we calculate the edge length of the body-centered cubic. So this L is equal to 4R over the square root of 3, and that formula was given to you. The edge length, so notice this is a cube, okay? So the volume is still going to be equal to L cubed. Volume is equal to length times width times height, right? But how do we know what L is? We can calculate L from the radius of an atom like this, okay? You know that the Pythagorean theorem says that c squared is equal to b squared, a squared plus b squared, right? So we're going to call that L, okay? So if we look at this triangle going straight through the center of this body-centered cubic structure, then we can say c squared is equal to b squared plus L squared, okay? So also, we know that in terms of the radius of an atom, C is equal to 4R. I can't draw on this because it's the book and I don't have this on the PowerPoint. So I'm going to you guys are going to have to bear with me here. But you don't have to do this derivation. I'm just showing you how they got the number, okay? I'm showing you how they got this formula here, but you don't have to do this derivation. You're just going to use the formula. This is the formula for a body-centered cubic, okay? All right, so remember, the simple cubic, the edge length, these atoms were touching, so the edge length was just 2R. Body-centered cubic, these atoms are not touching. These purple atoms are not touching. So we need to be able to calculate the edge length in terms of the radius of an atom. Okay, so for body-centered cubic, this is the way that edge length was calculated. The formula was calculated, okay? So from the Pythagorean theorem, we've got c squared equals b squared plus L squared from this triangle, okay? We also know that c, the edge length, is equal to 4 times the radius. So in terms of the radius, we could say c is equal to 4 times the radius because we've got the radius of one atom here, 2 times the radius of an atom in the center and the radius of another atom here, okay? So if you're curious about the derivation, okay? Now, we can also say that B is equal to L squared plus L squared because we have another triangle over here that is L and L, okay? So B squared is equal to 2L squared, so we can plug that in here, okay? So we're going to plug 2L squared in for B squared, Okay, we're going to plug 4r in for C. So we get 4r squared equals 2l squared plus l squared. And then if we solve for L, we get L equal 4r over the square root of 3. So that's the length of the side of one side of this cube. And remember, the volume is still L cubed because this is a cube. Okay, but since it's body-centered cubic, it's different from the simple cubic where we had 2r for the edge length. This edge length is 4r over the square root of 3. But you've got your formulas up here, so you can just look that up. You don't need to derive this equation, okay? And then I want to go down to the face-centered cubic and cover how they got those formulas real quick, okay? So face-centered cubic, remember this was also on our list. Let me go over here. All right, so face-centered cubic, we've got 4 atoms per cell. We're going to look at that in just a minute. The coordination number is 12, okay? So this is still a cube, and our edge length in terms of r is 2 on the square root of 2r. The packing efficiency is 74%. Okay, so we're going to look at how they got those formulas, or that formula. So here we can say that b squared is equal to l squared plus l squared, okay, which is equal to 2l squared, okay. And then we've got b is equal to 4r because that's 4 times the radius of an atom. So if we plug in 4r equals 2l squared, so they just, you know, move the numbers around to get the optimum thing that they wanted. And then solve for L, we can say that L is equal to 2 times the square root of 2r. Okay, so that's how we find the edge length of a face-centered cubic. So what you're going to be told is this is a simple cubic or face-centered cubic or body-centered cubic structure. Find, you know, the edge length if the radius is this or something like that. So you'll be told what formula to use. So you have 3 different formulas, 3 different options on the cube structure, okay? So our coordination number is 12. Also, we've got 4 atoms per unit because if you notice here, the cubic structure is embedded into these atoms. There's only 1/8 of an atom at the corners, okay? So that makes up 1 atom from that. And then we have 1/2 an atom at 6 faces. Okay, so this is a very tightly packed structure. So that gives us 1/2 times 6 and 1/8 times 8. And so that gives us 4 total atoms per unit cell. Okay, so hopefully that's making sense. All right, so if we go back over to our formula, we see that the simple cube is 1 atom per cell. Here's our structure. Coordination number 6, edge length in terms of r is 2r, and our packing efficiency is 52%. Body-centered cubic, 2 atoms per cell. Here's our structure. Coordination number is 8. Edge length is 4r over the square root of 3. Packing efficiency 68%. Okay. Face-centered cubic, 4 atoms per cell. Here's our structure. Coordination number is 12, and the edge length in terms of r is 2 on square root of 2r. Packing efficiency is 74%. So the face-centered cubic is the most tightly packed. Okay, so now we're going to work some problems based on that. I think that was basically all the information that we needed. Let me go back and make sure. So let's define packing efficiency real quick. All right, so calculate the packing efficiency of a simple cubic unit cell. So the packing efficiency is equal to the volume of an atom divided by the volume of the unit cell. And that's because there's 1 atom in this unit cell, right? Remember the simple cubic unit cell over here, okay? 1 atom per unit cell, okay? So to calculate the packing efficiency, if we can calculate the volume of the atom and divide that by the volume of the unit cell times 100, we can get the packing efficiency. Okay, so we're going to do a little bit of mathematical manipulation here. Okay, So we need to calculate the volume. So what we're going to do, we don't have any numbers. Notice that we don't have the radius of an atom. We don't know what the radius of our atom is. That's probably going to throw some people off at first. They're going to be a little bit confused. But if you take this formula and you say volume of atom divided by volume of unit cell, it turns out that the radius is going to cancel out. Okay, so the volume of an atom is equal to 4/3 pi r cubed. Okay, because the atom is spherical. Okay. And then we calculate the volume of the cube in terms of the radius. Remember that the volume of the unit cell is the edge length times, the edge length cubed. So we know that the edge length was L was 2R. So we want everything in terms of R. So 2R cubed, okay, and so that's going to be 8R cubed. So we've got volume of atom and we've got volume of unit cell. And then we could just calculate the packing efficiency, the volume of the atom divided by the volume of the unit cell times 100. Okay, that's 4/3 pi r cubed over 8r cubed. And I'm going to work the next one out by hand. I just thought I'd run through this one on the paper. Times 100, and then the r's are going to cancel, and you're going to get 4 over 24 pi times 100, which is going to come out to 52.36%. Okay. So you were actually, that's the packing efficiency of that simple cubic unit cell. So to calculate the packing efficiency, you have to have the volume of the atom divided by the volume of the unit cell times 100. Okay, and so the volume of the atom is going to be the volume of a sphere, and the volume of the unit cell is L cubed, and we have to get that in terms of R. Then divide volume of atom divided by volume of unit cell times 100, and you can actually calculate that out because the r's cancel. Now, if the r's didn't cancel, you would have to have the number for R, right? So we're going to do practice 13.2, calculate the packing efficiency of the two-dimensional lattice shown here. Okay, so hopefully this is not too confusing. I know it's not. This particular problem is not that simple, right? This particular problem was kind of challenging. All right, so we've got, all right, calculate the packing efficiency of the two-dimensional lattice shown here. I forgot to put myself some room in here. All right, so let's pull up, okay, here we go. I'll have to do it all over here. All right, so this is for practice. Um, 13.2, okay. Is that the one? Let me see. Yeah, calculate the packing efficiency of the two-dimensional lattice shown here. All right, so I've got packing efficiency equals to, remember, the volume of the atom divided by the volume of the unit cell. Okay, but this is two-dimensional. Okay, so we've got, instead of volume, we're going to have area. So packing efficiency is going to be equal to the area of the atom, because that's two-dimensional, divided by the area of the unit cell. So that's the only difference. So let's look at it again. Right here. Instead of volume, we're going to have area. And it's just like the simple cubic cell. The radius goes from the center of one to the center of the other, and the edge length is just going to be 2R. Okay, so just keep that in mind. The edge length is 2R, and so the area, okay, the area of an atom is going to be the area of a circle, so it's going to be pi r squared. The edge length is going to be L squared. I'm sorry, the edge length is going to be 2R, and the area of the unit cell is going to be L squared. So let's write that right here. So let's put that here. So the length, okay, is going to be this radius and this radius. And that's going to be 2R. Okay, the area of an atom, since it's a circle, is going to be pi r squared. And so remember that there's one atom in the simple cubic unit cell. Just because this is flat, we have one flat atom here, so that means it's going to be the area of that circle, which is pi r squared. All right, and the area of the unit cell, okay, is going to be L squared. All right, so now we can calculate the packing efficiency. This is times 100. Okay, so we've got the packing efficiency is equal to the area of an atom, which is pi r squared, divided by the area of the total unit cell, which is 2r squared, because remember it was L squared and an L was 2r, times 100, which is equal to pi over 4, because this r is going to cancel, and we're going to have, 4. And we're going to have, this is going to be 4r squared, right? And then the r squareds cancel, and we end up with pi over 4 times 100, which is equal to 78.5%. Okay. Hopefully that makes sense. All right. So relating unit cell volume, edge length, and atomic radius. Okay. So a body-centered cubic unit cell has a volume of 4.32 times 10 to the negative 23rd cubic centimeters. A body-centered cubic unit cell, this is a particular one, has a volume of 4.32 times 10 to the negative 23rd cubic centimeters. Find the radius of this atom in picometers. So in other words, from the volume, we have to get the volume from the edge, from the volume, we're going to get the edge length. And then from the edge length, we can get the radius. So from the volume, we can get the edge length from that formula. And from the edge length, we can get the radius from this formula. And that's because this is a body-centered cubic unit cell. So if we go back over to here, we see the edge length is equal to 4r over the square root of 3. So for our body-centered cubic unit cell, these are all cubic unit cells. So for all of them, the volume is going to be equal to L cubed for all of them. Okay, so the volume is equal to L cubed. L is equal to 4r over the square root of 3. Okay. So we're looking for the radius of an atom in picometers. Okay. So L is equal, let's go back. Volume is equal to L cubed. Okay, so L is equal to the cube root of the volume. Okay, so L is equal to the cube root of this number up here. And that was 4.32 times 10 to the negative 23rd centimeters cubed. So L is equal to 3.50. Oh, I left some digits off here. 88 times 10 to the negative 8 centimeters. Okay, so now we have the edge length of that cubic unit cell, and we can find the radius, because remember, L is equal to 4r over the square root of 3. We got that from this formula. We were told it was a body-centered cubic. Okay, and so we could solve for r if we multiply by the square root of 3 and divide by 4. So r is equal to, if I got enough room here, let me write it over here. So r is equal to L times the square root of 3 over 4. So I just solve for r, okay? So r is equal to the square root of 3 times 3.5088 times 10 to the negative 8 centimeters divided by 4, which is equal to 1.5193 times 10 to the negative 8 centimeters. Now, I was told to find that in picometers, and we were given cubic centimeters, so now we have to convert. All right, so 1.5193 times 10 to the negative 8 centimeters. And 1 meter is 100 centimeters. And 1 picometer is 10 to the minus 12 meters. You can look these conversion factors up. That's 152 picometers, okay? Roughly, approximately. Okay, so from the volume of the cubic unit cell, we were able to find the radius of the atom in picometers, okay? All right, so next we have, oh, that was that one. For practice 13.3, okay? For practice 13.3. I think we've got about 5 different types of problems. Let me see. Example 13.4, which is pretty long. For practice 13.4, we got about 3 more problems here. All right, so an atom has a radius of 138 picometers, okay, and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? Okay, an atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell? So we know that volume is still L cubed, because for all of these, volume is L cubed. For this one, we know that L is equal to 4R over the square root of 3. And we got that because it's body-centered cubic right here. Body-centered cubic, 4R over the square root of 3. Okay? All right. So L, so we know the radius. Okay? So from the radius, we can get L. Okay? And then from L, we can get volume. So from the radius, we can get L, and from L, we can get the volume from L. I think that's the way I was supposed to write it there. All right. So let's erase that so we'll have more room. All right. So let's start by finding L. L is equal to 4R over the square root of 3. That's the formula we got earlier. Is equal to 4 times 138 picometers over the square root of 3, which is equal to 318.70 picometers. Okay, so now we have L, so we can find the volume. The volume is equal to L cubed, because it's a cube, is equal to 318.70 picometers cubed is equal to 3.2369 times 10 to the 7 picometers cubed. Okay? All right, so we were asked to get it in cubic centimeters. That's probably the most challenging part of these problems, is getting all these conversions right, making sure you got the right units. Okay? So 3.2369 times 10 to the 7 picometers cubed, and 10 to the minus, let's erase this, let's write this neater, okay? All right, this is a tricky one. 10 to the minus 12 meters, okay, is 1 picometer. Now we know that, but notice our units don't cancel. I'm going to change colors here so you can see what I'm working with. Our units don't cancel because this is picometers and this is picometers cubed. So we got to cube the whole thing. Cube the whole thing, okay? And that way our picometers, once we work this out, they're gonna cancel, okay? And then we've got 1 centimeter cubed. We've got to cube the whole thing, even the number, is 0.01 meter cubed. Okay, so 1 centimeter is 0.01 meters, and you got to cube the number 2 so that this all works out. Okay, so that our units will cancel. All right, so I'm going to go ahead and, ooh, I don't know if I have room. I was going to write all of these numbers out, but I don't know if I have room. I'll go over here and do it on this next sheet, okay? This is going to be kind of confusing, but I'm going to go back and write the answer on the previous sheet. Okay, so what do we know? We go at 3.2369 times 10 to the 7 picometers cubed, okay? And notice here, 10 to the negative 12th meters cubed. I'm going to work that out. That's 10. That's 1 times 10 to the negative 36 meters cubed. All right, and then obviously 1 picometer cubed is 1 picometer cubed. I'm just getting rid of the parentheses. Okay, so 1 centimeter cubed is 1 cubic centimeter, had 0.01 meters cubed. Okay, so we got 1 centimeter cubed, and then we got 1 times 10 to the negative 6 meters cubed. Okay, so now our picometers will cancel, our meters will cancel, and we're left with cubic centimeters. Our answer is 3.2369 times 10 to the negative 23rd cubic centimeters. Okay, so I'll go ahead and write that back here. 3.2369 times 10 to the negative 23rd cubic centimeters. Okay, so if you have cubic units, then you've got to take your regular units and cube them with the coefficient. Okay, cube the coefficient also. All right, the next problem is example 13.4, relating density to crystal structure. Aluminum, now this one is a little bit more challenging, okay, because you just gotta think about what you got, okay? Aluminum crystallizes with a face-centered cubic unit cell. The radius of an aluminum atom is 143 picometers. Calculate the density of solid crystalline aluminum in grams per cubic centimeter. So density, remember, is mass over volume. Density equals mass over volume, and our units of density are usually gram per milliliter, and a milliliter is equal to a cubic centimeter. So generally, if you've got a liquid, you're going to go milliliters, and if you've got a solid, you're going to use cubic centimeters. So density is given in grams per cubic centimeter, okay? This sounds a little bit challenging, but you can use that information that you know to do this, okay? So we're given R, find D. Okay, so the conceptual plan is based on the definition of density. Since the unit cell has the physical properties of an entire crystal, you can find the mass and volume of the unit cell, and that'll give you the density of the entire substance, okay? So density equals mass over volume. That's going to be the mass of the unit cell. We got to get the mass of the unit cell, okay? We're going to get that by number of atoms in the unit cell times the mass of each atom. So we got to calculate the mass of one atom, then multiply that times the number of atoms in the unit cell, okay, which is face-centered cubic. Okay, we got 4 atoms in the unit cell. If you go back over here, face-centered cubic, 4 atoms in the unit cell. So we got to calculate the mass of an atom and then multiply that times 4. That's going to give us the mass of the unit cell. And divide that by the volume of the unit cell, which is going to be the edge length cubed. Okay, so I'm going to go over here and work the problem so I won't run out of room this time. All right. All right. All right. So I've got R is equal to 143 picometers. I want density is equal to grams per centimeter cubed. Okay, so that's going to be the mass of the unit cell in grams. Okay, divided by well, the mass of the unit cell in grams, that's actually, let me rewrite that. That's going to be the mass of the atoms in the unit cell times the number of atoms. I'm sorry, no, the mass of each atom. The mass of one atom times the number of atoms. One atom times number of atoms. Okay, so that's our mass divided by the volume of the unit cell. Okay, and the volume of our unit cell is going to be L cubed, edge length cubed. The edge length for a for this particular, this is our face-centered cubic, it's going to be 2 on the square root of 2 times r. So let's write that in. L cubed here, we already know is 2 times the square root of 2 times r, okay? And r is 143 picometers. Okay, so we can easily calculate, oh, that's cubed. We can easily calculate the volume here, but now the trickiest part is getting the mass of one of the atoms, okay? So let's go ahead and calculate that. So the mass of an aluminum atom is equal to, or if we go over to the periodic table, you see aluminum is 26.982 grams per mole, okay? So let's write that in. 26.982 grams per mole of atoms. But we need the mass of one atom because we know we have 4 atoms per unit cell. 4 atoms per unit cell right here, okay? And we need the mass of one atom, and then we're going to multiply that times 4. All right, and so we know 1 mole is equal to 6.022 times 10 to the 23rd atoms. So now moles cancels, and I've got grams per atom. So if I work that out, I get 4.48 times 10, 480 times 10 to the negative 23 grams per atom. This is the mass of one atom in my unit cell, okay? So the mass of the unit cell is going to be 4 times that. That's 4 atoms. So that's 4 atoms times 4.480 times 10 to the negative 23 grams per atom. Okay, and so now my atoms cancels and I'm left with grams, and that's equal to 1.792 times 10 to the negative 22 grams per unit cell. So I could even write atoms per unit cell here. Okay, grams per unit cell. So that's the mass of my unit cell. So I can put that here. And now I can calculate the volume of my unit cell, okay? All right, so I can just go ahead and calculate L is equal, the length is equal to 2 times the square root of 2r, and my r was 143 picometers is equal to 2 times the square root of 2 times 143 picometers is equal to 2 times the square root of 2 times 143 times 10 to the negative 12 meters, because 10 to the 12 meters is a picometer. Okay, so all right, so that's L. I have that written down wrong. L is equal to 4.045 times 10 to the minus 10 meters. Okay, so that's L. So the volume is equal to L cubed is equal to 4.045 times 10 to the minus 10 cubed meters. I'll just write meters cubed. Okay, so they went ahead and converted that to centimeters right here. Let me go ahead and I'll go ahead and do that. All right, so we could go ahead and say 1 centimeter is 1 meter. Okay, I'm sorry, 10 to the minus 2. I meant 100 centimeters is 1 meter. 1 centimeter is 10 to the minus 2 meters. Okay, and then you can cube the whole thing. This is the way your book did it. Okay, you could work it out the other way. I think I'll do it both ways. 6.618 times 10 to the negative 23 centimeters cubed. So they went ahead and converted it to centimeters and then cubed the whole thing. They took the edge length, converted it to centimeters, and then cubed the whole thing. Okay. All right, so now we've got the volume in centimeters cubed. So all we have to say is density equals mass over volume equals 1.792 times 10 to the negative 22 grams per 6.618 times 10 to the negative 23 centimeters cubed equals 2.71 gram per centimeter cubed. And if you look up the density of aluminum, that is actually about what you'll get. So from the radius of an aluminum atom, you can calculate the density of aluminum because you know that it crystallizes in the face-centered cubic crystal structure. So that's actually the density of aluminum. Okay. So hopefully that makes sense. I got this number here. I went ahead and converted it to centimeters and then cubed it. You could have just, yeah, that's the easiest way to do it. So really we should have said right here, we should have went ahead and converted it to centimeters right here and then plugged it in for L cubed. Yeah, we could have done it that way. All right, so is that the last problem? No, we've got one more problem in this chapter, 4 practice 13.4. Okay, and that's, let's read that one. I think that's the last one. Oh, we've got 13.5, but that's not a math problem. Okay. For practice 13.4, chromium crystallizes with a body-centered cubic unit cell. So this one right here in the middle. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. So kind of the same thing. Chromium crystallizes with a body-centered cubic unit cell. The radius is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. So this is body-centered cubic. So that's different because we're going to have the edge length in terms of R is 4R over the square root of 3. So that's going to be the only difference. We still have to find, the volume is still going to be L cubed. So we have to get L in terms of R, okay? And then plug that in, okay? And then calculate mass over volume. So it's worked exactly the same way. So we got chromium. Okay, so we have to look at the periodic table, and chromium is Cr, element number 24. That's 51.996 grams per mole. Okay, so 52 grams per mole, we can say. All right, so the R is equal to 125 picometers. All right. Density is going to be grams per cubic centimeter, so those are the units we need. Chromium is equal to 51.996 grams per mole, or your book uses 52.00 grams per mole. Remember, volume is equal to L cubed, and L for this one is 4R over the square root of 3. I got that from this chart right here, 4R over the square root of 3, because it's body-centered cubic, okay? So the mass of a chromium atom is equal to 52.00 grams per mole. Okay, 1 mole is 6.022 times 10 to the 23rd atoms, okay, is equal to 8.65350 times 10 to the negative 23 Okay, moles cancels, and I've got grams per atom. Okay, so the mass of the unit cell. Okay, I've got 2 atoms per unit cell. 2 atoms. Okay, how'd I get that? From this chart right here. 2 atoms per unit cell for the body-centered cubic. 2 atoms times 8.63. Oh, I think let's see, 8.653. I've got my numbers transposed somewhere. I've got 8.6350 times 10 to the negative 23rd here. Let me calculate that back out so I'll have the right number, because I got my numbers transposed. So that's 52 divided by 6.022 exponent 23. 8.635. Okay, so this was not 5.3, this was 3.5. Okay. All right, so that's 8.6350 times 10 to the negative 23 grams per atom. Atoms cancels, and that's 2 atoms per unit cell. So that's equal to 1.72, I think that's 70 times 10 to the negative 23 grams. Let's write that better. Grams per unit cell. Okay. Okay, so that's the mass of the unit cell. So we've got mass. Remember, density is mass over volume, okay? And we need our volume in cubic centimeters. So we can calculate the volume. Volume is equal to L cubed. And the L for our unit cell, for the body-centered cubic, L is equal to 4R over the square root of 3. So we just need to calculate L from the radius that was given. L is equal to 4 times 125 picometers. That's our R, divided by the square root of 3 is equal to 4 times 125 times 10 to the minus 12 meters. So we're going to convert that to meters, divided by the square root of 3 is equal to 2. You could have gone straight to centimeters if you knew the conversion factor there. 8868 times 10 to the minus 12 meters. Now I've got the length in meters. I need that in centimeters, cubic centimeters. They went ahead and did it the same way. The volume is equal to 2.8868 times 10 to the minus, that's not 10 to the minus 12, that's 10 to the minus 10 meters. Okay, 10 to the minus 10 meters. 1 centimeter is 10 to the minus 2 meters. Okay, so meters canceled, and we're going to cube that because volume is equal to L cubed. That's equal to 2.4056 times 10 to the minus 23rd centimeter cubed. Now you could have just gone here, converted that to centimeters, and then cubed that. Okay, in fact, we could just probably do it that way. Let me just cross that out, and I'm going to do it that way. Okay. So our L is equal to, I'm going to move this number right here down here, 2.8868 times 10 to the minus 10 meters. Okay. Now I want to convert that to centimeters. 1 centimeter, 10 to the minus 2 meters. Okay, let me do it that way. Let me check all my numbers here. So I'm going to go back up here and check this number too. So that's 125 exponent minus 12 times 4 divided by, that's 5 times 10 to the minus 10. I need the square root of 3. Square root. I don't have a good calculator, guys. Square root of 3 is 1 point. That's 1.732. I'll write that over here. 1.732. Okay. So 4 times 125 exponent minus 12 equals, divided by 1.732 is, that's right, 2.8868 times 10 to the minus 10, divided by 1 exponent minus 2 equals, so I got 2.8868 times 10 to the minus 8. That's our L. So now volume is equal to L cubed is equal to 2.88. I should have been able to do that in my head. 68 times 10 to the minus 8, and I got to cube that, is equal to, let's see here, where's that on my calculator? I don't see my power button. This is where not being in a classroom is a disadvantage. I would just ask the students to calculate this out, so I'm not seeing my power button here on this calculator. Where is it? I haven't used it in a while. Well, I'm assuming it's going to be the same thing as what we got up there. So that's 2.4056 times 10 to the negative 23, okay, centimeters, okay? All right, so that's centimeters cubed. So that's our volume. Okay, so now to calculate the density, we just need density equals mass over volume, which is equal to 1.7270 times 10 to the minus 22 grams per 2.4056 times 10 to the negative 23rd cubic centimeters, okay, which is equal to 7.18 grams per cubic centimeter, okay? So that's the density of this chromium, okay? All right, so that's how you would do that. Since they gave you 2 of those problems, I'm assuming that they're important, that they're going to ask you that again, okay? So classify, I'm going to go ahead and work these problems real quick, and then I'll move on. I may not do too much more today. All right, classify each crystalline solid as molecular, ionic, or atomic. Okay, so gold is a metal and therefore it's an atomic solid. Ethanol, okay, is a molecular compound. Okay, you got to freeze it. It freezes at a pretty low temperature, but anyway, if you froze it, solid ethanol would be a molecular solid. That's the alcohol that people drink, ethanol. Calcium fluoride, CaF2, is an ionic compound, so it's an ionic solid. So what type of atomic solid is gold? What type of atomic solid would be an atomic solid? Metallic, I guess they're getting at? Metallic atomic solid, because gold is a metal? I think that's what they're asking. Okay, so you know what? I know that we have 30 minutes left, but I have worked all of the problems from this chapter, and I think I'm going to let you go for today and pick up here next time, because it shouldn't take me too long to go through. I really shouldn't do this because I really need to finish this chapter as soon as possible. That's going to put me behind. I'll tell you what, I'm gonna cover just a little bit more material, guys, and then I'll let you go, okay? I'd like to get through as much of chapter what is this? This is 13, as much of chapter 14 as possible next week, because we're just a tiny bit behind. We're supposed to be covering a chapter a week, okay? So I'm trying to stay ahead so everybody gets their homework done. So I'm going to go ahead and cover this information about different packing structures, okay? So we can have different types of packing in these unit cells. And you'll see an example of that in just a minute. So we're going to see some pictures of that. But anyway, with spheres, it's more efficient to offset each row in the gaps of the previous row than to line up the rows and columns. So what we're looking at here is just a little bit larger picture of what these unit cells look like. So this is the closest packed structures. This is called closest packed structures, okay? So the second layer of atoms can sit directly over the atoms in the first layer, and this is called an AA pattern. And that would be if they were just lined up like the simple cubic structure, they're just sit right on top of each other. And obviously that's not the most efficient. But if the second layer sits over the holes in the first layer, this is called an AB pattern. So we don't have any problems with this, but you may get some questions with it, okay? So that would be AB, where the second layer sits over the holes of the first layer. Okay, we're going to see yeah, so that's like this right here. So this hexagonal closest packed structure, we've got layer A and layer B, where layer B, the center one is sitting over a hole in layer A. Okay, and this center thing looks like a hexagon. So that's called hexagonal closest packing. And here would be kind of an example of that. We've got this hexagon, okay, with a different arrangement in the center. And this actually is our unit cell. This with the lines represent the unit cell. Okay, I'm not going to go into a whole bunch of detail here. It's really not that important. Here we have a face-centered cubic unit cell structure. Okay, and that's going to be, this is the hexagonal closest packing, right? And that's actually face-centered cubic. Okay. So they're just talking about some different ways they can pack. Okay, the different ways that they can kind of offset each other and that sort of thing. Really, I don't think you've got any questions with this, so it's not really that relevant. Okay, this would be like an ABA structure. So basically you could have them sitting right on top of each other, or you can have the bottom one sitting on holes on the top one, and that would be called a closest pack structure. Okay. Oh no, this is cubic closest pack, not hexagonal closest pack, so I got that wrong. So here's our cube. Okay. So these are just different packing structures. Okay. So let's look at classifying crystalline solids, and then I will let you go. This is kind of fairly straightforward. So crystalline solids are classified by individual particles that comprise them. They can be either molecular, ionic, or atomic. So that's kind of what the problem we did earlier. Atomic solids are classified by the kinds of attractive forces holding them together. They can either be non-bonded, metallic, or network covalent. Okay, so let's look at this chart. So crystalline solids can be molecular or ionic or atomic. Okay, so they can be molecular if there's something like water, if they're like alcohol, if frozen ethanol. So let's say, you know, something like frozen ethanol, that would be CH2, CH3, OH. That would be ethanol. That would be a molecular solid if you froze it. You could freeze benzene, other molecular solids. These are just more like usually going to be like organic compounds, like a wax. A wax would be a molecular solid. It's an organic compound, but if it's frozen at room temperature, then it's a molecular solid. Okay, so the composite units are molecules. The example you're given here is ice. So water is a molecular compound, and because it's made up of molecules, and if you freeze it, then it would be a molecular solid. These have lower melting points. So even something like wax might have a melting point of like 100 degrees C or 80 degrees C or whatever, but those are relatively low melting points. Ice has a melting point of 0 degrees C. Okay, or you can have an ionic solid like table salt. This is going to have a melting point in like 1200 degrees C, I think, something like that. So ionic solids have high melting points. That's going to be, so here we've got sodium chloride. Okay, we could have potassium chloride. Okay, something like that. We could have sodium fluoride. Okay, that's what they put in toothpaste. So you can have just different substances like that. Okay, those are ionic solids. They have high melting points. They are made up of cations and anions. So all of these are crystalline solids. Okay, they form regular crystal structures um, in as they form solids. Okay, so atomic solids, these are going to be comprised, the units are atoms. Okay, so you could have non-bonding. So this would be like solid xenon. If you froze this noble gas, they're not bonded together, they're just held together by dispersion forces. They have very low melting points. Or something like gold, so a metal, that would be like aluminum, gold, silver, all right, any of the other metals. Or you could have network covalent. This is a little bit more confusing. Okay, and that's going to be something like glass, like quartz, like this is silicon dioxide, held together by covalent bonds. Okay, that's different from the molecular solids because this is not a small molecule. This is a network of covalent bonds. Okay, so that's a little bit harder to differentiate. So so molecular solids, the lattice sites are occupied by molecules, and the molecules are held together by intermolecular attractive forces like dispersion forces we talked about previously, dipole-dipole interactions, hydrogen bonds. They're very weak, and that gives them relatively low melting points. Okay, so like ethanol, if it crystallized and formed a solid, it's going to be attracted to other ethanol molecules by hydrogen bonding, forming a network, forming kind of a crystal network. Okay, but these are relatively weak forces, so the melting point for ethanol is like, I don't know, negative 50 degrees C or something. I don't know what it is. So some crystallize in different structures called polymorphs, okay? And this is important in pharmaceuticals or food chemistry. So here's some examples. Benzene, toluene are molecular solids. They just have dispersion forces, and their melting point, this one is 5.5 degrees C, negative 95 degrees C, okay? So chocolate is an example of a polymorph, and I'm just going to cover this and then I'm going to let you go, okay? So a polymorph, and this is interesting. So let's go down here a little bit. So chocolate can, it's not listed here. It's in your book. Okay, so let's go over to your book and look at chocolate, and then I'm going to let you go after we talk about chocolate. So it's a polymorph, meaning it has different possible crystal structures. Okay, so it can crystallize into different structures. And so a lot of metal alloys are like that. They can crystallize into different structures. Okay. But chocolate is a good example. And your book also gives you an example of a pharmaceutical that was used for treating AIDS. Okay, so it's this compound here. So so some molecules crystallize into polymorphs. Different crystal structures can have different properties, okay? And so it's important because it can have pharmaceutical variations, and this will be important for all you pre-med guys. So ritonavir was among the first drugs found to be effective in treating HIV and AIDS, and it was approved for use, but at the time only one polymorph was known. But after it began being used, so like if you stored this at a different temperature or something, it could change into a different polymorph. Its crystal structure would change, and the second polymorph was more stable, making it less water soluble and much less physiologically active. And even worse, small amounts of the second polymorph in a sample, if it converted to that, could convert the active polymorph into the less active form. So they had to pull it from the market and actually study it a little further and found out that they had to switch it to a gel cap that was refrigerated or a stable tablet in order to be able to put that back on the market. So chocolate is an interesting structure because it forms different polymorphs. It forms at 17.3 at the melting point of crystalline structure 1. So it has these 6 different polymorphs, okay? Is 17.3, 2 is 23, 3 is 25.5, 4 is 27, but the ideal one is 33.8. This is closer to body temperature. This polymorph has a firm, good snap and a smooth, shiny surface. And because its melting points around body temperature, it's going to melt in the mouth. Okay, so it's what you want. This is the crystalline structure that food scientists or people in charge of melting chocolate try to get. Good cooks do this. So if you have a different polymorph, you can get a bloom on the surface. So if you put your chocolate in the freezer, it can change crystal structures and give you this bloom. So in order to get the chocolate to the right crystal structure, what food scientists do or cooks do is temper it. So they're going to heat it up beyond the melting point of um, that particular polymorph. Then they're going to cool it back down below the polymorph. This is going to give them a mixture of crystal structures, and then cool it just to right above the melting point of the polymorph that they want, which is number 5, and then let it cool to room temperature and it'll be ready. Okay, so that's the way that this process is done. Okay, so that's all I'm going to talk about today. I'll pick up here next time and finish up this chapter and then probably start chapter 14 when we meet again on Tuesday. Okay, do I have any questions before I let you go? I'm going to go ahead and stop the recording.